defect TQFT. So here's the plan. I had no idea like what the audience would be precisely, and it seems like a rather mixed audience, in particular part of an audience that will be bored for my first few slides. So then look forward to the fire alarm, so actually have events that you can have in. So I start with a brief recap of TQFT and what extended TQFTs are, and what the ingredients that I actually want to talk about, like defects, and then put together defects of extended TQFT. And the example that I want to discuss are Rozansky Witten models, so twisted three-dimensional gauge theories with not gauge theories, sigma models, and in my case, the target is very simple, so an affine target P star Cn. We reduce the covariance hypothesis in a constructive manner in this example, so that means construct like everything that you want by giving the image. Here's again what I want to do now in a slightly different version, or this is what I want to do. So TQFTs are functors, and in my case, I would like to discuss a category of Bordisms, where the Bordisms can have corners, like in extended TQFT. So we want to associate something to stratified Bordisms that also can have corners, and then there are different labels attached to this, like a sample Bordism. So the two-dimensional patches are labeled by some objects in the target category, and then there are one-morphisms that carry labels of the one-morphism. There are one-dimensional submanifolds that carry labels of the one-morphisms in the target category, and kind of bubbles that look slightly too big here. So they are supposed to be points or two morphisms. And then what we want to do is like to explicitly know how to decorate this Bordism, and also how to evaluate the functor on it, and how what it means, what the result in the target category is. And so that in particular means that I have to discuss the target category, and that, as I mentioned, is a target category that has something to do with Rozansky-Witten models. Okay, so here is the boring slide, I think. So let me quickly remind you of the definition of closed TQFT in a kind of, way that, I don't know, something mixed between mathematics and non-mathematics. So what is a closed TQFT? So I want to talk about two-dimensional TQFTs. So these are functors from a category of Bordisms that have one-dimensional manifolds as objects, and interpolating Bordisms as morphisms. So in the two-dimensional cases, there actually is this a pointer. Work, no, right, it's working. There was something. Maybe. Yes, there's something. Okay, great. So the objects in the two-dimensional case would be circles or disjoint unions of circles, the morphisms, two-dimensional Bordisms between them. Then there's a target category that in most traditional applications as finite dimensional vector spaces, but that I would like to replace by some Rozansky-Witten category in my talk. Then Z is a symmetric monoidal functor between these two categories. So in particular, this target category needs to have the required structure, so some monoidal products and gradings and so on. Then if in the traditional way to look at these things, one views this circle or what one wants to associate to a circle as a kind of state of space, space of states V that you can imagine to get by canonical quantization on a small column. And then there's a monoidal unit in that category. If it's the vector space category, then it's just the field, or here the complex numbers. So that's what I would associate to the empty set on this Bordesen side, and then to disjoint unions of n circles. So the monoidal structure on this side gets mapped to the monoidal structure on the other. So here's again like a picture how to evaluate such things. So what did I talk so far? So we talked about circles. So they are objects in a category. They get mapped to, for example, vector spaces if the target category is vect. The disjoint union gets mapped to the tensor product. And here are some samples of what is going on in two-dimensional TQFT. So in particular, you have pairs of pens that you may read as maps from the disjoint union of two circle to one outgoing circle. And then on the other side, that gives rise to some product that goes with vector space into an algebra. And then, for example, this thing would be a map from V tensor V. So two ingoing circle, outgoing would be the empty set. So this would read a map from V tensor V to C. And there's an identity on the circle that just looks like this. So it's just this cylinder built on the circle. And then there are relations. So there's a kind of associativity relation for this product. Okay, let me discuss one-dimensional TQFT where objects are 0 dimensions and the morphisms are one-dimensional. I want to give everything an orientation. So there are two versions of points, plus labeled plus and minus, and there's also the empty set in the category. And then we can draw all morphisms between them. And here's again some list from which you can build. Yeah, so I omitted the grading, but in principle you can build any other morphism from these basic ingredients. So I always read pictures from right to left, and then I read this thing as an evaluation and that as a co-evaluation. So because this thing takes point disjoint union with points and maps to the empty set. So in case of vector spaces, you would map this to an actually evaluation, like you know it from vector space. And here the co-evaluation goes the other way from empty set to disjoint union of the two points with different orientation. Then there are identities that look like this on a single point. And if you have several points, then that's the identity. And then there is a gluing relation, so a snake relation that tells you that if you glue these two guys together consistently, then that should be the identity. So in particular, if I have a 0 plus 1 dimensional TQFT, then the TQFT is completely fixed once I have given the image of the point, so of one of the points. So let's say I give the image of the point labeled plus in the target category. I need that in the target category. The object that this is mapped to is dualizable. And then the evaluation, the thing needs get mapped to the evaluation in the target category, and the co-evaluation to the co-evaluation, and so on. And everything is determined by these ingredients. Okay, so now let me speak about extended TQFTs. So far I talked about things in dimension D-1 and dimension D, and kind of like semi-explained how this works in the case that D is 1 or 2. But in a extended TQFT or fully extended TQFT, we want to consider manifolds of any codimension in one picture. So in particular, we start in the lowest dimension, so we can start with points, much like on the previous slides, and they can be continued. They can be connected by lines. So those are would be the one morphisms. And then if I have a bunch of lines, then they can in turn be connected by two-dimensional surfaces. Yeah, and so on in principle. So in my talk, I will stay at the two-dimensional level, but you can talk about the structure in three dimensions. So then there are again kind of basic building blocks, as well as gluing relations that you have between them. And this whole structure is captured by a higher category. For us, it's the two category. So let me start again in the lowest dimensions and say a few words of what is going on in 0+1 dimension. So this is similar to the picture I had before for the 0+1 dimensional TQFTs. So we now want to associate something to points in the target category that I still have to talk about. So U has to be an object in the target category, and we imagine that we associate it to a point. Then we need that this object in the target category has a dual object so that we can talk about evaluation and co-evaluation and so on. And we also need a monoidal structure in that target category. And then U is dualizable if there exists evaluation and co-evaluation like this. So again, read right to left. This is again the map from dual point to empty set, red and or it's the image of that in the target category. So we have a map, we need to have a map evaluation from U tensor U dual into the monoidal unit and also co-evaluation map. And then such that, again, you can pull these snake lines that I had, so this line, such that you can pull it straight, so that in this case, it means that there needs to be an isomorphism. So the geometric picture I have in this picture at the bottom, and this snake line that comes about if I combine evaluations and co-evaluations, and then it needs to be isomorphic to this thing at the top. So that is the identity on the objects, and then there is an isomorphism between this bottom and this top, so read bottom to top, and that's called the cusp isomorphism, and it's a two-morphism. Yeah, that basically, yes, that interpolates between these two configurations at the bottom and at the top. And there are two versions of it that are drawn here. Okay, so then we have more building blocks and more surfaces. So I talked about the evaluation and co-evaluation in 0+1 dimension. So that's, for example, this thing would be evaluation. And now I consider evaluation built on this evaluation. So let's take this thing and let's take its dual thing. So this is thing together with its dual, and now we want to make this an evaluation. So we want to map it to some identities, to an identity, and this identity on 2 points. So this is a map from 2 points to 2 points, and so to formulate an evaluation on an evaluation, we would like to map this to that, and the way to map it geometrically and in the Bodism category is to put some two-dimensional interpolating surface that I try to draw in this picture. So this is some saddle shape in case you are not happy with my artistic abilities. But anyway, so it is, looks like this at the bottom and like this at the top, and the whole thing looks like a saddle and is called the evaluation on the evaluation, and it's a two-morphism. I think I have better pictures just on the next slide, where I put all the adjunction two-morphisms together. So here's again the evaluation on the evaluation that I explained in more detail on the previous slides. And then there are similar things in the same spirit. So for example, this is a co-evaluation on a co-evaluation because it now starts here at this empty set and it goes to this together with its dual that then comes glued together as a circle. So that ingredient, and so we can build these this cup and this cap, which is another version of this, and there's this inverted piece of the saddle as well.
What are the tildes on the symbols?
The what? The twiddles thingies? Ah, yes. So I kind of omitted a little bit details that there are two versions of evaluation. So there's the evaluation on the object and kind of on the dual object, and I have points and dual points distinguished by plus and minus referring to an orientation, and then the evaluation and co-evaluation refer to on this object or its dual object. Yeah, so I'm a bit, I don't want to go into the detail of like distinguishing all these tools and so on. Right, and then there's again such an S condition on all these ingredients, so ignore these labels, so they are in the, they refer to the target category that I have not yet discussed properly. So here everything is made from the pieces you saw on the previous slide, or rather you saw this one on the previous slide and that one on the previous slide. So they are some evaluations on co-evaluations and so on. And then there are these half cylinders, and I didn't have them on the previous slide because they are just identities again. So we have this piece, so it's some co-evaluation, and then we just move it up in the other, so like this, and so this reads identity on what is at the bottom. So all the cylinders are identities. So this is an identity, that. And now if you glue these things together, it gives you a gluing relation that needs to be satisfied. So it's again some S figure that, if you look at this, looks like it needs to be the same. I mean, topologically the same as this half cylinder. Okay. Good. So we have this higher category of Bodisms from points and lines and so on. And now we need to formulate a functor. I already on some of the slides said this, but let's summarize this here. So we need this extended TQFT that's supposed to be a functor. So between this Bodism category and a target category of appropriate structure. And then the co-Bodism hypothesis says that there's a one-to-one correspondence between these fully dualizable objects here and extended TQFTs, taking values here. So we need a target category, and we don't want it to be vect, but we want it to be something else. And here's again one of these written. So you see very well the pictures that I made myself and the pictures that other people made. So here's a self-made picture. Our target, our higher target category is motivated by a defect category, and here's a picture how higher target category coming from defects look in principle. So the objects are theories. So for example, as part of the data of the theory, there are some bulk fields that I do here, and then there are codimensional one defects that separate these different theories. So in this picture, they are surface defects, and then on the surface defects, you can have line defects, and on line defects, you may have local operator, and then this whole thing assembles to a category. And in our situation, we want the theories to be the images of the points, and the domain balls the images of the lines in this category, and then the line operators to be images of the surfaces. Okay, so here is, so of course, the example that I want to study is of this type. So let's talk about this affine Rozansky Witten model and what the corresponding category is. So the objects are a list of variables. So I use the notation. So I have, for example, n x variables, and we use the notation x underlined to just refer to this bunch of x variables. In a physical three-dimensional n equals 4 series, you may think that these are, n is the number of hypermultiplets. And these variables are, yeah, half of these hypermultiplets. Okay, so in the bulk, we put list of variables, so they are the objects of the category. Then there are surface defects, and they carry two labels. So one is some extra list of variable restricted to the surface and not inherited from the bulk, and another thing that we associate to the surface is a polynomial. It's called W because it's basically a super potential. So if this is a 3D n equals 4 theory, I want that the two-dimensional defects have 2,2 unbroken supersymmetry. And then one way to give such theories is via a superpotential that is in the surface variables, so the two-dimensional variables, but then there's also a coupling to the bulk variables that is allowed. Okay, I have two such things in my picture. So this surface defect maps between these two theories, and then there's this other one labeled by other variables and and the appropriate bulk variables like this. Okay, so let's summarize this again on the slide. So we look at the theory of three-dimensional n equals 4 hypermultiplets, and the scalars are maps from three-dimensional manifolds to T star Cn. And we topologically twist this supersymmetric series. And then the objects are list of variables of this category. The surface defects are extra variables together with a superpotential, so a pair of like this, so extra variables and superpotential. Then there is an invisible defect that basically glues the bulk variables together in a trivial way, such that if I move it on top of any other defect that doesn't, it leaves the defect alone. I will come back to this on the next slide. So it looks like this. So it's a specific, so a set of variables A, and then it glues together X and Y variables on the two sides of the defects like this. And the notation here is that if I take product of these n variable things, it means to sum over all variables like this. Okay, then I need higher morphisms. So the line defects are matrix factorizations of differences of superpotentials on the surfaces, and then there are local operators that are natural maps between such things. So these are some twisted complexes version. I don't want to go into it, but it's a category that is under good control. And then altogether, one can show that the truncation of this category is a monoidal 2 category, and all objects are fully dualizable. By truncation, I mean that I truncate and consider only classes of matrix factorizations and don't try to look at a 3 category. Yes.
So here that you're building interfaces or domain walls by adding 2D chiral multiplets and then coupling them to the bulk with a superpotential.
Yes.
Is it not possible also to add a 2D gauge multiplets and consider a GLSM that couples to the bulk fields?
Yeah, so there are various different things one can do. So one thing we have been thinking about is like to gauge this whole thing. So to add some transformation properties to the bulk fields as well, and then to set up.
But here I'm okay with having the bulk.
Yeah, so you want to have, yes, so that would be part of it, so that the bulk fields transform trivially, but then you add something to the surfaces. So I'm always in this twisted situation, so I wouldn't actually add a vector, but would only see any remaining gauge symmetry part by making things equivariant. Yeah, so we would add that and impose that the superpotential is invariant and things like that, yes. So that's actually part of this bigger category that I was referring to. If you just impose that the bulk fields are transformed in the trivial representation. And then, yes, then to look at, instead of a category of matrix factorization, equivariant version of it. Yeah.
So if you left the bulk empty, general 2D defects would support 2-dimensional B models, which if the B models have compact targets, would be dualizable TQFTs, but if they don't, they might not be. Like they wouldn't have finite partition functions or finite dimensional state spaces. And so I guess you don't want to allow arbitrary coupling with the 2-dimensional matter and gauge fields. Here you're restricting to you're restricting to just some particular set, right? I guess you're
Yeah, so I mean, the reason that I truncate is of course that, so what do I do? Well, two-dimensional surfaces, so what in a fully extended sense, what would I associate to two-dimensional surfaces? Well, it would be the state spaces of the 3D theory, and they are still, so this can be infinite dimensional as long as I don't want to look at the next level in the categorical sense.
So part of that question is like you're okay with the 2-dimensional interfaces having infinite dimensional state spaces.
Yeah, so that's, yes. Yeah, maybe I say this, I have a slide later saying what these state spaces are. You can maybe say this again, it's related to this truncation business that I do here. Okay. Any other questions? If not, then I put this picture again. So I like to say something about the composition of one morphisms. So we had that the one morphisms correspond to these domain walls with extra variables and superpotentials. And then how do we compose them? Well, we just move one on top of the other. And then what happens is that these surface variables, so the A and B variables, are surface variables of the result, and there are also these squeezed in Y variables that are also surface variables, and X and Z variables are source and target, and the superpotentials add up. So there's this composition law between the morphisms that makes sense. Now is in here, yeah, is nicely captured in this defect sheet. Okay. So let's talk about dualizability and how far we go. The objects of the key theory are lists of variables, and their duals are again the same list. And dualizability means that there exists evaluation and co-evaluation for each such object, and then we need that those in turn have duals. Okay, so what is the evaluation? I think, why didn't I? Okay, so let me jump to the next slide. In between, so the objects were these lists of variables, and then there's a monoidal structure where we just take two lists together like this on the level of objects, and there's a monoidal unit that is the empty set. So let's move to this slide again. If I want to make some evaluation, it's supposed to be something that goes from this list X prime together with X to the empty set, and its form is the X giving extra variables and the superpotential. And now for all these evaluations and co-evaluations, it's always the superpotential, the form of superpotential remains the same. It's just that I view this pair in different ways. So here it's from all variables to the empty set. So physicists may also think about a folding trick that allows us to see this as a boundary. And then for the full evaluation, it's the same thing going in the other direction. And then this glued together thing is isomorphic to this line, and you have seen a picture of this isomorphism as a two-dimensional surface, and this now is a two-morphism, and it corresponds to in this category an explicit matrix factorization of the superpotential plus that minus that one. So one can give this explicitly, which I won't do. So here's again this, this summary. So one morphisms are these pairs, and two morphisms are isomorphism classes of matrix factorizations. So that's the truncation, and then the statement is, or one can prove that this is a symmetric monoidal two category. And I didn't talk about the braiding, but it's again some given explicit matrix factorizations. And all objects here are fully dualizable. Okay. So what does it mean? So we can now compute anything, at least on the level that we have been talking about. So in a topological subset up to dimension two for these affine Rozansky Witten models or models under equally good control. So for example, there is this state space that we can compute by gluing stuff together. So this lower part here is some co-evaluation, and then this part in bracket is like these cylinders are identities, and then there's saddle and inverted saddle and so on. And we can just, so since we have our target category under complete control, we can just evaluate this composition. And now here's what comes out. So genus G, so two surfaces we associate in our category matrix factorization. So that was what the two-dimensional things are. And in our case, also if it's a closed surface, then it's a matrix factorization of 0. So from empty set to empty set, and so that's a complex, and we can compute its cohomology, and then its cohomology looks like this. So it's a polynomial ring and 2 sets of variables, and then there is a piece that contains some fermions. So this is Z2. So the matrix factorizations have a Z2 grading, and this shift 1 refers to the odd grade. So what is it? So we were talking 3 hypermultiplets, and so the scalars make up this polynomial ring, and the fermions turn into vectors after twist, and they give rise to, for genus G surface, to this piece. Okay, so now I truncated at isomorphism classes of matrix factorizations, and you see here that in the highest dimension that I can compute, so that's 2 dimensions, and if these are closed surfaces, they give rise to vector spaces, and because my target was non-compact, this vector space is actually infinite dimensional, and so infinite dimensional vector space would not be dualizable, and that was part of the reason why we had to truncate. But it's totally fine to have these spaces in 2 dimensions, and we don't even talk about maps between them. And if we did, we could still talk about isomorphisms, just not glue them back in place. Okay, let me talk a little bit about addressing the Bordisms with some defects. So in my first slide, I had some defect data. So there were bulks and codimension 1 defects and codimension 2 defects, and we can put them on the Bordisms, and we look at, in this way, can look at stratified Bordisms and label the different strata by the defect data. And the defects, inherit, or this is basically what I already talked about. So they also satisfy such dualizability conditions in our target category. And there are also other, so to make everything consistent, there's also kind of this data that geometrically allows to pull the defects to a back of a surface and lets us do the same. So there are these isomorphisms that, so here's some evaluation at the bottom, at the front of this half cylinder, there's this defect X, and at the back there is just nothing. So just the identity on this thing that is carries the bulk label V. And then that's supposed to be isomorphic to a picture where this is on the other side. And a similar picture for the opposite cylinder. Okay, now that we have also this defect data, we can evaluate things, stratified Bordisms. So anything like this can be turned into a completely explicit formula in the target category. And basically there's a graphical calculus, and you just developed by these people developed by these people that we can now apply, and it allows us to read, for example, this piece just as the bottom to top. So there's some code evaluation on this X3 thing, and combined with an evaluation, this phi2 is put in between. So we can compute, and instead of computing this one, though it looks very nice. I just prefer to compute something for which we may have a better interpretation, or where one can see a bit from a physics perspective what is going on. So, for example, we can look at boundary conditions. So what are boundary conditions? Well, they are just special kinds of defects between a theory and some empty theory. And in our language, or in our example, a defect was labeled by extra variables and a superpotential. And here I put extra variables gamma and a superpotential gamma times z, and z are the bulk variables, and I read it as a map from the empty set to z. And then this is a perfectly fine diagram that we can evaluate, and we evaluate, and the result is again a matrix factorization of 0 and of gamma, so a polynomial ring in, compared to the sphere, it has half of the variables, and we interpret it as imposing Dirichlet conditions on the z variable. So it's precisely the state space you would expect in a theory of free fields where you put Dirichlet positions on. Okay, so indeed we can build a fully fledged open-closed topological field theory valued in this other target category. So that means we have some open sector. So we have disks, and we have open string pair of pairs like products. And like one thing that is always nice to look at is the bulk boundary map. So there is this diagram, so it maps from the state, so from the space that we associate to the disk. So in our case, it's not a vector space, but it's a certain superpotential, or with it also the matrix factorization of it. And with it, you may also regard this as a kind of isomorphism classes of line operators of the bulk theory. And then we map it. So we include one of these boundary defects in this picture and evaluate the functor on it. So this is supposed to be the target category. So and then that gives us a little bit unconventional bulk boundary map. Since we have made sure in our category that all pictures, everything can be deformed consistently, or like part of what we have already proven. I guess it might have been a bit hidden, but part of what we have proven that this is like that this target category has nice features, and it in particular means that we automatically have, without further ado, like some analog of open-closed TQFT with consistent Soring relations, including a one-loop condition that can be called Cardy's condition. And if it were in a geometric context, it's the Riemann-Roch theorem. And what does it state? It basically states so that that if we glue together, if we glue together two such bulk boundary maps, or the bulk boundary and the boundary bulk maps, that we can read this in the open channel. And one can say that gluing together a generalized notion of quantum dimensions. So these quantum dimensions are now not dimensions, but they are spaces. So it's one level higher up. We can interpret this as like in something in the open string sector. So it's now not an intersection number like for an ordinary Witten index, but it's again some space. that we can associate to it. Okay, so for the, so yeah, since I should say baby Hirzbuch, Riemann-Roch, so if one does it, if one could do, or if one were to do this exercise for more interesting target geometries, then this would possibly be more interesting and case. Yeah, it's clear that this diagram factorizes consistently, but it's geometrically maybe not the most interesting thing. Okay, so this brings me to my last slide. So what did I try to explain in this talk? So I kind of discussed a certain two-category formulated from Rozansky Witten models. I think I didn't give credit to Kapustin and Rozansky, who first formulated part of the structure of this category. So sorry, I should have done that, but let's do it now. And so once we have this category, we can apply the cobordism hypothesis systematically. By this, I mean that we can construct a unique extended TQFT for each object. So in our category, the objects were distinguished by a number n that was the number of hypermultiplets. And once we have that, we can compute anything, for example, state spaces on any orientable or oriented, in fact, surface with or without boundary. We can include defects and evaluate anything also on stratified Bordisms. The physical theory has various symmetries, so there's still a leftover R symmetry even after the twist, and there are flavor symmetries. I didn't talk about them, but it's straightforward to implement them into the discussion. It just means that all these state spaces we have computed get some grading, and we can drag along these symmetries. We can also discuss them more, and in particular, so there is in this target geometry T star Cn, we have some SP symmetries, and all these symmetries can be implemented by defects. And one can give the explicit defects for each of these symmetries. That also means that we can, for example, put some defect networks on the surfaces. So I showed you how to compute state spaces on the torus, and you can like dress this torus with any defect network of these symmetries, and again compute the state space and see what comes out. And indeed, in this way, what one models in this way are flat background gauge fields. So they are only background gauge fields because I didn't do an orbifold construction, but just can talk about putting some generic defect networks. So that means putting a background gauge field and so on. So I did talk a little bit about boundaries and an open-closed TQFT and how intersection numbers get replaced by spaces. Then indeed equivariant models are possible, and we are currently discussing them, and they would lead to gauge theories and more general targets of weighted, so T star Pn, and you can adjust like different weights for the individual coordinates and possibly also look at Grassmann versions of this for non-abelian groups. Okay. So 50 minutes, I think. And thanks for your attention.
In this formalism, so you've shown the state space of a disk with a boundary condition. So in this formalism, could you obtain somehow the state space of the sphere by taking two such disks and somehow summing over all possible boundary conditions, like gluing in some sense those two half spheres?
Well, I can punch out two boundary conditions from a sphere. But yeah, so I can look at the sphere, and that's indeed this intersection number that one can compute. But then to sum over all boundary conditions, you first need to say like what all boundary conditions are, for example. And this I am not sure. So in any case, it's not built into the formalism or anything. So you would have to say what are, yeah. So in some sense, one can of course make a list, at least in this model, and to sum them, but it's not something particularly or better implemented in this formalism.